We are happy to have Professor Dr. Reader Julia Gog here from all the way from Cambridge, and she has been here before at the institute, so coming back for this weekend or week. It feels like a weekend because we're celebrating, but for this week and the special day to give a talk yesterday, but also today about immunology, diseases, and the title here is Math versus Disease. Welcome, Julia.
Thank you. And thanks very much for the invite. This is fun. So I'm going to talk about maths versus disease.
Can we switch to the next?
Can we switch over to the laptop? With slides, excellent. I know there's a suspicious number of experts here, but I'm going to talk for a general audience, and all you experts, just relax and enjoy it as a general audience thing, okay? So this is the maths department in Cambridge, Centre for Mathematical Sciences. I was promoted to full professor a year ago, so I'm still excited every time I see it at the moment. Santiago commented on mathematical biologists. We're a little bit cooler than just mathematicians, right? So any mathematical biologist, you know this story. You meet someone at a party and they say, "What do you do?" And you say, "I'm a mathematician." And if they're brave, they say, "What kind of math?" Then you can say math bio, and you see this visible relaxation, right? And you can start to talk about what you do. And then you have this discussion where you actually explain, maybe it's not what they expect you to do. So here's me, here's what people imagine I do. So I think about viruses, yeah? That's a bad cartoon of a flu virus. I think about epidemics. This is seasonal influenza in humans in the UK. And I think about how disease travels between places. Does anyone know where I've got this from, this picture? I'm glad someone else also plays iPad games. This is Plague Inc., a fantastic iPad game on disease spread. Okay, so I think about all these things, and somehow I do some magic with maths and put it all into a mixer, and I come up with a prediction, right? 42 years to next pandemic. So that's how the conversation, the party's going. So you make predictions about pandemics. You think, well, if we could, we would. But it doesn't quite work like that. What I actually do, of course, I think about all these things. I think about viruses, I think about epidemics, I think about spatial dynamics. We can't just say, right, next pandemic will be exactly this date. It's not how it works at all. The kind of things we do, of course, is we build simple and usable models. The simple is often necessary for the usable. We work with experimentalists, so we're not just some boffins in some back room doing our own thing. Well, sometimes we are when we're doing this. But sometimes we join in with labs and do sort of very practical things. Mainly we're trying to unpick what's happened in the past. We can't even think about prediction if we haven't understood what's happened yet, right? And identify what we don't know. What is it we're missing? Have we really understood the past? What do we need to know next to improve our knowledge? And I think I'm going to talk mainly about these middle two things, give you examples of these to give you a feel for what it is we do. I'm going to jump across lots of different scales. So we're going to start with a single virus particles, so very tiny. I sort of feel like if I come to a math bio celebration, especially the first math bio day, and I do not introduce the SIR model, I'll be struck down by lightning by the end of it. So we'll have to do this bit of classic epidemic theory. And then we'll think about the pandemic of 2009 and how it spread through the US, so through one country. So different scales. Ready? Yes. There's no M&Ms, I'm sorry, but there will be interaction.
No voting.
No voting. No. We start there, we get to there. Single virus assembly. Okay, so another cartoon of influenza virus. Quite often we're thinking about the surface proteins and how they appear to the immune system. You've got this shell, and the whole virion is just a package for bringing its genome around and getting into another cell, right? So this time, we're going to think about the genome of flu virus. Flu is unusual. It's a segmented virus. So rather than being one long stretch of RNA, it's RNA rather than DNA, it's actually 8 separate segments. You could think of those as little tiny chromosomes, right? The numbered segment 1 to segment 8, be grateful for that, because the numbering systems beyond that in virology are not good. They've even sorted them into size, just reverse order for reasons I don't understand. And each of these, this is what you need to know for this, each segment is a recipe for something that the virus needs. For example, segment 5 is the blueprint to make the main type of surface protein, the hemagglutinin. Segment 6, I think, is the neuraminidase, the other surface protein which is not as abundant. Segment 1 of 7 and 8 is the matrix protein, which is part of the spherical shell. They're all necessary, right? And if one of those is missing, something is going to go wrong for the offspring of that virus particle. Does that make sense? Okay, the cartoon's about to get worse. Here's my version of flu virus, because I'm really just interested in this genome inside. So I've got these 8 different colours here. Now think of a massive cell, and this cell is probably like a cell in our respiratory epithelium, so a surface somewhere in your airways here. Virus goes in. We won't worry about that process. It unpackages. The whole point of the virus is it's going to make use of the cell's own machinery, actually in the cell nucleus, to make more copies of its own genome, and also to translate its genome to become these proteins and these structures it needs to be more virus. All right, so you've got more copies of the genome, virus bits, then automagically it makes new virus, and off they go to infect another cell. And, okay, I can see a few biologists smiling at me a bit. Yes, I know, but this is the bit we need for now. The mysterious bit we're going to think about is this process of how do you package to make new virus particles. So the virus needs one of each of these 8 segments. If it doesn't have them, something goes wrong. How does it do this? And I'm presenting this in a hopefully a simple way, but this was a problem that was running in virology for some time. And for a long time, this is one of the hypotheses, this so-called random packaging strategy, so possible strategy. Pick at random. So I'm a virus particle budding off a cell, and I just grab 8 segments and hope for the best. Yeah? So this virus particle, I don't know if you can see, maybe it's got 2 greens and it hasn't got a purple, that's no good. This has got 3 reds and it's missing yellow. But maybe once in a while you get lucky and get one of each of the 8. Now, so-called random audience, do you think this is a good strategy? No. So the fun you can have if you're talking to actually any audience, I'm going to do it with you guys. So it's quite unlikely to be successful, right? Is it better or worse than 1 in 10? Worse. Better or worse than 1 in 100? Worse. 1 in 1,000? 1 in 10,000? 1 in a million? So the fun thing is different groups of people have a different intuition as to how unlikely this is, right? Sort of intuition breaks. You sort of think if I grab 8 things, they're not going to be all different, right? You're going to get some doubles. You kind of know that. But how unlikely? Of course, we're going to use maths to sort it out. Start to put it into sensible format. We have a large pool of segments. Here they are. Large just means if I take one out, the pool is basically unchanged. Roughly the same number of each of the 8. So there isn't some weird, rare segment 1 or something. They're all equally there. And we pick 8 at random. Do we have a fully viable virus? That's a silly question. What's the chances of having a fully viable virus? So we go for a counting argument, all right? So ways of picking a random 8. So imagine I've just got a lucky dip of segments and I'm picking 8 different segments. Pick the first one, pick the second, so they're ordered. How many different ways can I pick from my big bucket of segments? You are allowed to shout today. How many different ways can I pick one segment? How many different ways can I pick two segments? How many different ways can I pick 8? 8 to the 8. Now let's see if you're going to go for the intermediate step. And what's that? Oh. Okay, so think in terms of powers of 2. So this is 2 to the power of 24. And everyone should know that 2 to the power of 10 is about 1,000. Yeah? So this is 2 to the 10 times 2 to the 10 times 2 to the 4. So yeah, let's go for 16 million. All right. And the crucial thing is these 16,777,216 possibilities are all equally likely in this weird setup that we've got. Out of those, which ones actually result in 8 different ones? So you play the same rewind. You play the same game again. You start by picking one segment. I've got 8 different ways of doing that. Now I pick the second one. How many different ways have I got of getting the second one? And then I keep going until I get to 1. Do not go to 0, right? Stop at 1. So then we multiply these together, and we find we've got 8 factorial ways of getting these. And if you're being cheeky, you ask the audience, how big is that? And the fun thing is, for school kids, they've been told that factorials are large. They say, it's massive! You say, is it bigger than 16 million? And you see the clunking going on. It's about 40,000, so in some sense it's big, but it's also tiny compared to this, right? So the probability of having a full set, as you have seen by now, it's this number over this number, and everyone just wants to cancel down an 8, but you know what, it's fine as it is. You go ahead and work that out. It's 0.0024, which isn't actually that intuitive. 1 over that, the closest integer is actually 416. So those of you who started to get twitchy when I said, is it less likely than 1 in 1,000, you were right to start getting suspicious. It's pretty unlikely, but it's not 1 in a million. It's 1 in 416. Do you think viruses do this? Someone's trolling me. Well, 1 in 416 means most of your effort is wasted, and plus other things go wrong in virus replication. Even if everything else is perfect, this is a terrible strategy. So no, we don't think this happens. So you might then say, okay, right, so we're going to play a different game. We're going to be a virus particle. We're going to come off the cell, and we're going to pick segments until we've got at least one of each. All right? So this is how kids collect stickers, right? So, these World Cup football stickers, or there's Lego stickers, which are popular now in the UK. Actually, I think they're just cards. You keep collecting them until you've got a full set. You don't just collect exactly the number you need, and then you're sad because you've got duplicates and you're missing some. You keep going, right? Maybe viruses do this. So, what's the nicest way to work out the expected number of segments we need to package if we go this way? How many do we expect to need? And the trick there is to go sequentially as well. But this idea of we have total number of possibilities and we work out how many of those are successful, you can see that's not going to go so well, right? Because what are all the possibilities? Rather than picking 8, might pick 9, or we might pick 10, or we might pick 100. How are you going to count all of those? It's going to be a pain. So a slightly better, much better method is to work out one by one, how many do you expect to need until you've got the next new segment? So the first segment you pick, you definitely need it because you've got nothing, right? So with probability 1, you've got a new one, so the expected number of picks to get your first new segment is 1, yeah? And if you can understand what the expected number is for the second segment, you can sort the lot out. But the trick is to go to the last segment. Imagine you're in a situation where you've got 7 of the 8 and you're missing one of the segments. What's the expected number of segments you need to pick to get the missing one? Is that completely obvious? So I think there's a little phase when you've done enough maths at school that it's obvious, right? Because you've got a 1 in 8 chance for each go. And we know if you've got 1 in chance a 1 in 6 chance of getting a 6 on a dice. On average, you roll it 6 times on average to get a 6. So you decide that works, yeah? But if you know too much maths, you start to worry, oh, actually, this is a geometric distribution. I need to work out the mean of that. Okay, it's just 1 over p. We're fine. So you've got this phase where it's obvious, and there's phase you worry about it, and the phase that's obvious again. Is everyone in one of the obvious phases? Okay. So 1 we write strategically as 8 over 8. So what's the expected time to get to the second one now? 8 over 7. And does that feel right intuitively? Yeah, just a bit bigger than 1, because most of the time you pick another segment, it's probably one of the ones you need. Sometimes you need a second one, and occasionally third or more. So a bit bigger than 1 feels right. So you've got a 7 in 8 chance of getting a new one, so you expect 1 over that, 8 over 7, as a time to get a second different one. Third, at which point you don't have to think about it, you just got the mathematical pattern now, or almost symbolic pattern, and we go the whole way down to that last annoying segment, 8 over 1. And you add those up, and you get 21.7. All right, so you need about 22 segments on average. Is this a better or worse strategy than the random packaging? Yeah, I'd say it's better. So the random packaging was sort of inefficient by a factor of over 400. This is inefficient, rather than needing 8, you need 22-ish. So it's inefficient by a factor of 3. So this is kind of better. We've got some small problems where we might have duplicate segments, and we might have misbalanced gene expression, all kinds of problems, but almost works. We've worked out the expected number. Of course, you could work out the probability of having a full set, having picked a certain number of segments. And the only point we've really sorted out here is this one down here. This was our 0.0024 if we picked 8. And you can come up with a way of doing this. And those of you who study some probability, it's inclusion, exclusion. You can come up with a formula for probability of having all 8. And we've worked out the average time is about 21.7. But you can see it's got this nasty long tail. So, you know, if you've picked like 30, you've still got hefty probability of having not got the full set yet. And if you're trying to motivate this for youngsters, you change this problem to a far more tasty problem, right? Collecting anything, a set of 8 toys, where all 8 toys are equally likely. There isn't a rare one, right? And you take your nasty virus graph, segments picked, and you change it to something much more fun. And if you're feeling very brave, you do some actual experiment involving chocolate, but I'm not that brave to do the chocolate experiment. Okay, so hopefully that's shown you by quite simple arguments. Just on basic combinatorial arguments, you can see that random packaging is a truly dreadful strategy. Packaging more than necessary is kind of workable, but really not brilliant. So that kind of points at there's going to be some other mechanism. And I'm going to 2 slides talking about this. Specific packaging. There has to be something about each of these segments that labels them. I'm a segment 1, I'm a segment 2. Because these random strategies just don't work well. There's got to be some mechanism to be more specific when packaging. These labels we call packaging signals, for obvious reasons. And at this point, our segments are just RNA wrapped around sort of basically a cylinder. But the cylinder is the same between all these segments, so the signal must be in the RNA. It's the only thing that differs between them. Now, this is a horrific graph, but I'm going to talk through this. This is work we've done with the virology lab in Cambridge. This is a graph for segment 1 of influenza, which is 763 amino acids long. And for each of those positions, we grab all the data in GenBank and work out how much variation there is at that position. And this get-out-of-jail-free acts, as I put up here, after we factor out everything else that we possibly know about these things, we get a score for how much variation there is. 0 means no variation, and that's really suspicious. 1 means plenty. Individual low scores are nothing to worry about, but if there's a packaging signal, it'll be a contiguous chunk. So you're looking for a region where there are low scores. The red line is a moving average of width 10, just a way of picking out where things go low. this is one of the first projects I did after PhD. So my PhD was on the equations behind epidemic models. There was lemmas, there was theorems, there was corollaries. It was very mathematical. And then I started working on this with my friends. Where do you think a packaging signal is going to be in this segment? These dots down here are looking a bit suspicious. But you can't prove it. But it's worse than proof. You've got to be sure enough to go and send people you like to go and do a ton of work to check it experimentally. So to shift the mindset from I prove it to am I sure enough to tell the experimentalists it's worth a few months doing this was a bit of a shock for a mathematician to come from that to that. But indeed, it turned out to be here, and they could do very, very targeted experiments to try and find these things without having to look across the whole genome. And it worked. So that's an example of one of the things we can do using mathematics in infectious disease. No differential equations yet, just simple combinatorial arguments, which any mathematician could have done, but the trick is you then work with these nice virologists to do something with it. Okay, that was a little at speed, but that's an example of what we can do at the tiny scale. Who here has not heard of the SIR model? I can see lots of this. Okay, there are several of you. You can't see how many there are, but I think I saw 7 hands go up, so I'll go through it. So classic epidemic theory. So here we're thinking about big outbreaks, the plague, the big 1918 flu pandemic, which we're in the centenary of, and the 2003 SARS outbreak, which actually frighteningly, if you're talking to school kids now, you know what? They don't know about this thing 15 years ago, because that was before they were born. So everyone's forgetting about this one. The classic SIR model is a way of saying we take the whole population and we think about putting them into groups, into compartments. So S are susceptibles, I's are infecteds, R's are recovereds, and everyone goes into exactly one of those boxes. Everyone starts here. These ones have the disease and are infecting others. These ones have recovered with immunity, or they die. We don't care, we're mathematicians, they're kind of the same, really. They're gone. And there's only 2 actual processes here. There's infection, which takes you from S to I, and there's recovery, which takes you from I to R. And then we can look at this as a differential equation system. So dSdt is the rate of change of the number of susceptibles, so capital S is now a number of susceptibles. dIdt, drdt. We have it so that these add up to be n, and n is the total population size, whether that's 1,000 people or 1 million or whatever you're dealing with. The transmission comes out of S and into I, and the recovery comes out of I and into R. And I think I'm not going to talk about... Seriously, I could talk about this all day. That's the main thing, is there's something taking from S to I and I to R. And with that, you can run simple outbreaks. So here, I'm not plotting the R's, I'm just plotting the S's in this blue dashed line, I's infected in this red solid line. And this is a typical output you get simulating this. This is time. Maybe think about those as in months. So this is something like a flu outbreak. And you get some beautiful things. For example, you might say the number of S's should go to 0, but it doesn't. It plateaus out to some constant other than 0. We can do some mathematics to find what that constant is. You've got this epidemic curve, this so-called bell-shaped curve, though I've never seen a bell that looks like this. I don't know about any of you. It's also always asymmetric. It comes up a bit faster than it goes down. And you think, well, okay, I've read this in a textbook, and I actually read this in a textbook as an undergrad. I thought that's very nice, but it can't actually match what happens in reality. And here's a very classic data set of influenza in a boarding school. Boarding schools are great. They're closed, captive populations. So they knew the number of boys, it was a boys' boarding school, who were infected on each day. So the dots are the real data, and the solid lines are fits to that data. And for a model which basically only has 2 parameters, 2 constants that you can change, plus initial conditions, which we know how many boys there were, plus, well, there's another thing to be fitted there. It's not bad, right? Kind of gets the general shape. Kind of misses this drop at the end, but maybe things changed in here a little bit. So that's the classic SIR model, the compartmental model. It's a useful way to think about things where you can get some nice mathematical results. But you're all looking at this thinking, this is not how an epidemic actually goes. Actually, I realise everyone in this room is thinking differently why this isn't quite how things go. Here's my list of things that are missing, or approximated. The first obvious one to me is, well, actually, if you think about when you have flu, and mostly flu is the disease I think about, you go from being susceptible, you get infected. You don't sort of wander around, you're absolutely fine, then bang, you're ill and infecting others, right? That doesn't happen, does it? You know, there's a bit of time between getting infected and actually it builds up to a full-blown infection where you're actually obviously ill and actually infecting others. So perhaps there ought to be more subtlety between the S and the I, so we can fix that. As this model has been set out so far, there's no natural births and deaths in the system. We've got a closed population. It's fantastic for a boarding school, but not if we want to capture one country over a period of many years. There are new people coming into the system. There are people going out of the system. Infections aren't always just single phase. For example, think about HIV. You've got actually at least 3 phases for that. You've got the acute phase a few days after infection. You've got this latent period of being HIV positive, but not AIDS. And then you've got this period with AIDS. And that's not there. Spatial dynamics, we're going to talk about that. This has treated everyone like they're in one place. This idea of recovered is forever. Sometimes immunity is not lifelong, it's not perfect. This, what I've shown you, is a clockwork model. It's deterministic. Perhaps life is a bit random. Age structure, kids mixed together at school. I've got everyone here mixing. Virus evolution, there's more than one strain. I've treated it as one strain. And I'm sure if we went around the room, we can come up with 10 more things in this list. But despite that, this is still a really useful, basic idea to start from. Think of the population as SIR. When you're talking to disease modelers, we think in terms of this. We say, oh yeah, my model's basically an SI with one of these. Or it's a SEIR on a network, or it's a SIR with age structure. It's a language we start from. It's a common platform that we work from. Right, I'm now going to mess up the beautiful SIR by talking about some data, which screws up everything. Ready for the last bit? Big scale. The 2009 influenza pandemic, which no one has forgotten yet, right? Please. This is a big collaboration. I'm just going to present this as a single story, but lots of people were involved with this. This is quite a US-based project, and the data set comes from the US. So the data set is, well, we've had a few subtle comments about the US healthcare system. This is based on insurance claims by week, by zip code, by postal code that people live. It's the number of visits to outpatients doctors for influenza-like illness. This is not perfect. No one's actually done a swab and checked it's flu, but it should give you a signal of when flu is circulating. It'll pick up some extras as well. So here's the time series for the whole US for a number of years. It doesn't ever go to 0, and probably quite a lot of the baseline is things which are not flu, but basically when it spikes, it's probably flu. That sounds a bit hand-wavy. We've done a bit more work to verify that it fits with other data sets and is flu. We're going to focus on 2009 because we're interested in the pandemic. So just zooming in on that year, we've got January to December, and what proportion of doctor visits were for this flu-like illness. And you can see it's got this sort of triple bump, which wasn't like the other years. The other years were basically just one bump around here-ish. This is basically seasonal flu, normal annual flu that comes around happening. This was pandemic, and this monster here was also pandemic. But the beautiful thing about this data set is we can zoom down in more detail. So that's the same curve. The US, if we just look at California in red here, and New York State, which is in blue here, this is the curve for California with the whole of the US underneath dotted. And New York State in blue, whole of the US dotted. There's one really big difference. Yeah, I'd say that's the second biggest difference. There's a bigger difference, which is... Yeah. So California didn't really have a spring wave. The New York state certainly did. There's a shift in timing, and that's less surprising. In fact, every state has subtly shifted. California basically only panicked for a week. So there was news reports of a pandemic, and lots of people went to the doctor with, I might have a cold. So this, I don't think, is epidemiologically important. And you can have a look in the movie and see that for yourself. You can split it further to cities. So here's New York State. There's 3 upstate cities, and New York City is under this massive circles down here. So these upstate places, the curve in the background now is for New York State as a whole. You'll see Buffalo, not much spring wave. Rochester, not much spring wave. Syracuse, not much spring wave. And you can see the autumn waves are shifted around in different sizes as well. Whereas we go downtown, spring wave, spring wave, spring wave. So you've got spatial heterogeneity the whole way down. You can keep zooming in. And actually, some of these cities, we can zoom down a little further, but it gets noisier. The best way to visualize this, hopefully you can see this okay. The circles in different places proportional to the area, the area of the circle is proportional to the population in that place. So this big circle here is Atlanta, which has a big population. This tiny circle here is Dothan, Alabama, which has a smaller population. Big cities are many circles. They're just a bit of a mess. Colour of the circle is proportional to how much flu-like illness there is at that time in that place. Where's my cursor gone? And we just see what happens going through time. So April, May, June, July, August, September. It's gone, isn't it? Do you know, I can't get tired of watching this movie. There's always more and more to see there. There's more layers. But what I'd like you to have spotted there is that seasonal flu happens. The spring wave happens and is mainly up here. And then the autumn wave is just an explosion. Yeah? There might be a third wave here, but sadly our data set cuts out at that point. Okay.
Does the wave always go from west to east, not from east to west or not?
Luckily, we don't have data from many pandemics. In seasonal flu, it's complicated. But what happens here is not necessarily east to west or west to east. Did you see where it started from?
Well, Texas seems to start the big one.
Oh, I'll show you another slide, and then you can decide. So there's the orientation. We're going to focus purely on this monster here. This was the explosion, right, this autumn wave. And now you realize this is just an aggregated curve. It really doesn't capture what's happening. So here's 4 individual places. And I'm only going to care about the autumn wave, so the big spike, big spike, big spike. This is Trenton, which is the postcode that had Princeton in, which is where I was based while I was in sabbatical doing this work. This is autumn wave we're going to care about. They actually had a spring wave as well, but just care about this one. We decide when the onsets are, so we come up with a single date when we say it arrived in the autumn. And luckily, because it's spiky, we can do that and just sort of say there's a time there. Okay, so at each place, we're going to reduce it to a single date, which is time of arrival of autumn wave. I'm going to go back to the map. I'm going to colour in places, not by how much flu there is, but according to the time of arrival. So if it arrives in July, August, it's green, September, red, and through this sort of rainbow colour. I hope that's clear enough, yeah? So Atlanta, just to show you an example, is this curve, and you can see it is super early at arrival. And Boston, pleasing places A and B, right? Boston is a blue curve, and you can see, indeed, it's very late. And you've got this nice rainbow spread, right? And maybe it's easier to see from that, whether it's east to west or what direction it's going in.
Well, it starts in Texas and some southern states.
No. Red is later than yellow and green.
But there's a green one in Texas.
This is Corpus Christi, Texas. I don't understand why it's weird, but basically it doesn't seem to spread to other places. I think we've probably made a mistake in the detection dates, or it had an outbreak which didn't spread. So I wouldn't say that was the origin of the wave. It was its own little planet. But it gets worse than that. There's multiple origins if I show you the whole of the country. Right? So the east of the US is very nice. You might also worry there's no dots here. There are actually people there, of course. But the places are so small. If the places are under a certain size, I've just removed them because the data set is noisy. You can actually do better work and put them back in. But you can see there's some natural centres. There's a green, yellow, red coming out from there. There's a whole thing going on in California, Central Valley. And yeah, you've got weird outliers, Corpus Christi, Texas, St. Petersburg, Florida as well, which don't quite fit. As we were doing this, other groups were also publishing, but on a much smaller and simpler data set, just treating the US as 10 regions. And the things that made it into publication very quickly were correlating the influenza onset time with school opening. So when the kids go back to the school for the autumn, end of the fall break. Some places start as early as start of August. I think by law they all have to go back by the start of September. Red dots are for East US only, black dots are for the West, red line is East correlation, black line is all dots together. And yeah, highly significant correlation. Flu timing goes with school timing. If you can read the axes, can you see what's wrong with this conclusion?
What's on the y-axis?
The week that the flu arrives, according to this dodgy red dotted line that I fitted for each place, so that's it's American way round, so it's July 19th through to November 1st.
Also it's dates.
Dates, yes, in 2009.
Dates on both axes.
Yep.
Or what does that mean? Time is just, I don't understand what you mean.
Well, it might help if I put this identity line in, so 2nd of August, 9th of August, through to 6th of September. That's the identity, that if dots are on there, that would say when schools open, flu arrives. If the dots all lined up a bit above it, like here, you'd say schools open and flu arrives a week or two later. That's not what happens, right? It correlates, but it's not as simple as you open the schools and flu arrives. Okay, so that story's a bit sticky. We brought in, so other people have been saying, okay, it's just a spatial wave, geographic distance, and actually this is distance from that little town, Dothan, Alabama, which I'm so fond of. And if you do correlations from there, for the east of the US, it's amazing. For all of the US, yeah, it's still highly significant. These are largely the Californian dots, which come, if you put them in the right line, they should be sort of up in the roof, but they come earlier than you'd expect. They've got their own separate thing going on. Highly significant. So yeah, it's about geography as well as schools. And then people start to say, well, actually, the weather's important for flu. So absolute humidity in those places, measured in some way, influenza. Yeah, highly significant. Okay, so it's about schools and geography and weather. And you start to worry about your colleagues, right? Because this is the arrivals time map. You can sort of see the pattern. It's sort of south to north-ish, but with a bit radial. What spurious correlation would you like to come up with for this? I think you're all too polite to say, but you're thinking of one, right? And perhaps you can think of one indeed, which is sort of red dots down here and blue dots up here. Maybe some more blue dots over in California. Yeah, a map like this. You know what this is? So I took data from the 2012 US election, the percentage of people in that state who voted for Obama, and yes, highly significant correlation, at which point you really worry about your colleagues because they're like, oh, yeah, so you know, there's socioeconomic and political factors here. It's like, no, stop. Stop. These are all sort of compounded with each other. Maybe it's all one thing, and actually everything else just picks up a signal of that. So I'm going to blitz through this because I think I'm going to run out of time. You want to understand in more detail what's going on. So this is where we start to construct and test dynamic models. And no one likes seeing equations pictures, so here we're making models out of Lego. And actually, this is totally appropriate for this project. Here's me at the front, but actually it's Stephen Kistler at the back who's doing the heavy lifting and the hard work there. If anyone wants to know this outreach activity with Lego and children to simulate epidemics by picking them out of the population bag, and you might get susceptible, you might get a recovered, then you add them, and these curves emerge from this game. I'm happy to send you details of those. Anyway, model building. Decide which factors matter. Build them up to a transmission model between cities. So rather than thinking about number of people, we think about cities as being the units we work with. Probability of transmission between cities may depend on many factors, like distance between them, population sizes, like little places may be less important than big. Humidity has been thrown in as a hypothesis, so we keep it. Schools have been thrown in as a hypothesis, so we keep it. And you build up a model. This looks horrific, but it just does in mathematics what I've said in words. You build up a model with all possible options. And from that, you can build up to a probability of infection from one place to another. And, okay, I've got a model. I've got a data set. You could use your model to simulate it. Remember, it's a stochastic model, so you have to run it a lot of times. And then you want to see, does it match up with what's going on here? And of course, what we're actually doing is trying to adjust the parameters, like maybe increasing the transmission rates, decreasing how important schools are, to make this observation as likely as possible, i.e. find your best fit parameters, right? On top of that, you make all different possible combination of models. Maybe we switch off humidity as a factor and see is the model as good or not. And I think you can summarize this in 8 different types of model, which include local transmission, include schools effects, include humidity effects, and then this is where I've taken out the mathematics. Compare it to observed data, and I've given you a qualitative answer rather than quantitative. So which factor is most important? Yeah, so all these models that don't include local transmission are a terrible fit to data. The ones that do are okay or good. What's next most important? So if you don't include that, it's okay. No, hang on. Humidity, yes, no, okay, yes, no, good. So it doesn't distinguish by humidity. So what's the second most important factor then? Yeah, it's schools, right? So if schools are included, you get a nice fit. If they're not, it's kind of okay. But then once you've chosen those two, humidity really doesn't help things at all. So yes, it correlates, but it's all been explained away by other factors.
Excuse me, okay is sometimes rendered as all correct. So I thought okay was better than good, but it's not in your language.
Oh, okay, no, this is not British. British okay is definitely better than good. It's American, good, okay. I'll give you something more quantitative. And I love this graph in particular because I can camouflage with my shirt on this one. So my colleague Sebastian Ballesteros made this, and I said, those are disgusting colours. And I was wearing this shirt, and he said, but Julia, I see what you've done there, thanks. Actually, there's 400 models that we turn things on and off, and AIC is a measure of basically how bad things are. So these high bars are terrible, these are the good models, and you can come up with a measure and find that at the best end, you've got this model which includes spatial effects and schools effects, but no humidity effects. But no one actually likes looking at this for too long, except maybe me. To summarize what we found in words, we found exactly what you saw in the movie. It's really shaped by very short-range transmission. It goes from city to city. If you don't include that as being the dominant thing going on, you don't capture the pattern. It was almost a diffusion wave, right? There is occasional long-range transmission. You have to include that. California got infection from somewhere, right? There's a small effect of schools, small but statistically detectable. There's a small effect of population size. And humidity, I'm sorry, it's gone. It's just not relevant by the time you've taken into account everything else. It's a false correlation. Just because humidity correlates north and south, of course, it's going to correlate with timings. Political allegiance correlates north and south, but I'm pretty sure that's also spurious. Just to finish, to be honest, any research project is not we've done it, here's the answer, we are finished. This created a big problem, right? Because if we go back to this distance graph, great circled distance from Dothan, Alabama in kilometers, influenza onset by weeks, you can get a wave speed by looking at this eastern US line here. And you basically go 2,000 kilometers in about 13 weeks. And it's 22 kilometers a day. All right? Has anyone watched movies about pandemics and disasters and contagion and such like things, yeah? It doesn't take 22 kilometers a day in the movie, does it? It jumps around the world by plane immediately because we're so modern and connected, right? Do you know what? We're not. 2009, 22 kilometers a day. You can outrun it if you have to. 14th century bubonic plague, 4 kilometers a day. Yes, that's slower, but it's also a much slower disease. But the thing that creeps me out is these timescales, these speeds, are not that different. However, in 2009, the country was not in lockdown. The country was basically functioning as normal. All the airports were open, the schools were open, people were moving around as normal. Maybe they used hand sanitizer slightly more often. But I don't believe there were any major effects to really change behavior in 2009. This doesn't fit the picture of the modern world. I can't explain this, but it's been bugging me, and we are still thinking about this and taking more and more mathematical techniques to this problem. Sorry, I'm going to end with a problem, but that's how research goes. So we've looked at a number of different problems, from viruses, classic epidemic theory, through to a country. And I hope I've also shown you, as well as we don't just do predictions, we actually do other things to explore what's happened and help to work with experimentalists. We're also using a wide range of mathematics in these systems as well, in epidemics and infectious disease. There's loads still to be done. And I think I'll stop there.
Well, we have time for a few questions, so I start.
Now, if the 22 is correct, and maybe it's not, but then doesn't that mean that the flu is not spreading through planes, it's just spreading through, the good old stuff? Shouldn't that be your conclusion?
Okay, so just to repeat the question, make sure I've understood and others have heard it. Is the conclusion, if 22 kilometers a day is right, should we conclude that flu is not spreading by plane? I find it hard to believe there was no transmissions due to people flying by plane. There must have been people with flu who flew, travelling from A to B, who arrived and infected someone. That must have happened. But what it tells us is it wasn't important for then being the spark to set off the entire city. So there may have been transmission chains, even quite big ones, but they weren't the ones that founded the epidemic in a city. Somehow, epidemiologically, they're not important, even if they happen. And that still makes no sense to me.
Okay, next question. The Spanish flu of 1918 is a pandemic of kinds. The Spanish flu is a misnomer because it was only disclosed. What should it be properly called? The flu of what, South Dakota or whatever is it? And I have another question after that.
I don't know. It depends who you believe. Lots of people are still thinking about that 1918 pandemic and trying to find its origins. Probably it was circulating in humans several years before 1918. As Spanish flu, as you know, because there was a free press there reporting it. The same way this beastie was called Mexican swine flu. A load of old rubbish. It probably didn't originate in Mexico. It may have been first picked up there, but it's come from somewhere else. That's always the case.
Okay, so no answer. But then could you explain a little what you think about why the Spanish flu killed so many young people in reproductive age and not children and old people? Okay.
Here I'm only repeating what I know from reading other science and talking to other scientists. This is not my speciality. With the 1918, it was a really nasty pathogenic strain. But you know this classic W-shaped curve, that the very young, the very old, and a little spike in between had a high fatality rate with 1918. And part of the story there is probably there was something similar circulating to the 1980s. It was an H1N1 pandemic, actually the same as this one, same subtype, which was circulating prior to 1889 or 1890. It got wiped out and replaced by another strain. But do you know what? If you were born before 1889, you had some prior immunity, so you weren't going to get as sick. So that explains why the drop down the other end of the W. The rise up to the W, I'm just repeating the classic stories, which is almost the more healthy you are, the stronger your immune system, because of the mode of pathogenesis, your own immune system gets you in that one. It was a nasty. But it's not my expertise. Immune system overreacted, yes.
That was great, thanks. With I'm sort of captivated by this idea of 22 kilometers a day as well, or actually any speed, but especially with something like flu, which has such a high rate of genomic change. What is that? I mean, can you get like a base pair per kilometer, kind of? I mean, has anyone ever looked at the sort of spatial change of genomics?
Yes. So there's an emerging area, which you probably know a little bit about. It's got a beautiful name of phylogeography. Oh, okay. So phylogenomics is you make family trees out of viruses. You build trees based on the genomics. You just take all the sequences from GenBank or whatever, and you make some nice tree. Geography is geography. But if you bring those things together, you've got the property of a given sample is not only its genome, but where it's come from. And you can use phylogeography to try and reconstruct where things have come from. For example, in the Zika outbreak, there's lots of deep sequencing going on real time. There's beautiful portable sequences, so you can then try and say, where has this come from? If we look at this and try and work out, actually, it's come from this region, we need to go and pay some attention to this region. With the flu, actually, there isn't enough public sequence data for me to do very much during that autumn outbreak, amazingly. However, because I failed to get my hands on this, what Stephen Kistler has done, and we've just had the paper accepted yesterday, is reverse phylogeography. So we've put up our model of what we think happens, and we've put out a hypothesis of what the phylogenetic tree of these largely silent changes should be. So these aren't functional changes, but it should be possible to map back and test what we're proposing, which is risky in a weird way around, but it's the only thing we could do.
Where can I find them?
Epidemics. We've got to just edit the page brief, so give us a day or two. Or just email me, I'll send it to you.
So I've had just another short question. Thank you very much. And
Welcome.
I just missed the bridge, the Queen's,
Oh,
for romantic reasons. And so I know we have high school teachers among us here. So has any one of you done any SIR with your students? Can you tell us about that? If you get the mic from Santiago.
I had a group last year and a group this year. Thank you. I had a group of students last year and a group of students this year. And last year's students, I gave them the model, the differential equations, and told them how to implement, well, I basically explained Newton's step method, and they did that in Octave, which is the free version of MATLAB. This year I have a much brighter group, so I just told them that you will get an infection if an infected meets a susceptible, and some of these will be recovered. And they did their own equations. That's quite impressive. That's not a normal guy, really.
what age are your school kids?
Well, he's really, really bright.
These aren't 10-year-olds.
No, he's 18.
There's a lot of activities that can be done in schools for different age groups, and there's something about epidemics, well, it certainly captured me as an undergrad, but there's something about the idea of epidemics and contagion, these non-linear processes, but with a bit of drama, because they're disease, that can be good for capturing the imagination and sort of seeing how is this math used. Very sort of concrete output. They're great for schools' activities. Yeah.
Thanks a lot, Julia.
Very welcome.
Wonderful.
Thank you.